All right, so in this video, I'm going to demonstrate how to evaluate inverse functions when you're looking at the graph of a function. And I'm also going to show you how to kind of quickly graph an inverse function. So I'm going to, anytime I'm working with the function f of x, I'll use my black pen. And if I'm working with the inverse function, I will use my red pen. And that way we can kind of keep these things straight a little bit. Okay, so remember that a function is any relation that takes one input and maps it to one output. So you know, this is not a really common way of looking at functions, but it technically is a function. Check it out. This is a set with 3 points in it. It's an xy pair. So this is 3, 2, which if I were to graph it, black pen, this is our function, it would look like over here at 3 and then up 2. So that's 0.3, 2. All right, the next point is -1, 4. So I'd be out here at -1 and then up at 4. And then the last point is 4, -3. So we'd be here at 4 and then down to -3. And it'd be this point right here. Okay, so yeah, technically this is a function where it takes 3 pieces from the input, or 3 values from the domain, our inputs, which are 3, -1, and 4. And then it maps it to 3 different outputs, which are 2, 4, and -3. So just to kind of really clarify this idea, I'm going to go ahead and throw a map up here where this is my domain. And this other will be my range. And 3, -1, 4 are in the domain. These are all the inputs here. And then my outputs are 2, 4, and -3. So again, I really like using this idea of a function map anytime that I'm trying to understand inverses. Okay, so let's say you're given this is your function and here's a graph. And now they're going to say, hey, what is f inverse of 4? And that's the question. So how are you going to find this? Well, remember that when you're evaluating an inverse function, you're taking a value from the range and mapping it back to the domain. So essentially, if I want to know f inverse of 4, that's a matter of taking 4 from the range and mapping it back to its input from the domain. Now, what would that look like on a graph? Because let's say you're not really into, you know, drawing out function maps, or let's say it's not even an easy function map to draw. So how would you go backwards using a graph? Well, let's think about what we just did here. This is technically that point right there, where the input was -1 and the output was 4, so I could go -1 and then up to 4. Like this right here is the point that I'm talking about. So how could I have gotten, you know, this answer that it went back to -1 without using a function map? So think of it this way. When I'm looking at a graph, if I see an input to an inverse function like this, so 4, I want to think about this as the y value on my graph, and I'm asking you what is the x value on this graph. So my answer, I mean, kind of is a matter of switching these two values. So if I am asking what's f inverse of 4, that's a y value. I go up to here on the y-axis, and then I take a look at what the x value was on the x-axis. So for an output of 4, the input was -1. So that's how we can do that. Now, what you might have noticed, because with an inverse function, I'm going to take these away, technically, this is my input. This is technically an x value. I don't do f inverse of y, I do f inverse of x, right? F inverse of x, something like that. So if I wanted to write this as a point for my inverse function, this would be the point 4, -1. So again, like I was kind of getting at, you're switching the x and y values. So what used to be -1, 4 as a function value or function point is now 4 comma negative 1 as an inverse. So we switched them. So this is actually a clue to writing out our entire inverse function really quickly. Let's see if we can do it. Our inverse function would be the set of all these points where the x and y values have been switched. So rather than 3 comma 2, this would be 2 comma 3. And then instead of, well, we already did this one. Instead of negative 1, 4, this would be 4 comma negative 1. And the last one would be negative 3 comma 4. So here's my function in black. This is my inverse function in red. And essentially, all my x, y values got switched around in order to find my inverse function. So this is going to give us a method for finding inverse functions pretty easily. But before we go there, I want to actually graph these points and show you what our inverse function looks like when it's graphed. So if I went 2 comma 3, that would be this point here. So it was that one, and it went to this one. Okay. 4 comma negative 1, so that would be 4 out here down to negative 1 here. So this one maps down to that one. And our last one would be negative 3 and then up 4. So this one mapped over to that one like that. Okay, so we're going to continue looking at patterns of things as we start graphing our functions. So the next one we're going to look at, this was a discrete graph, right? Single dots on a graph. So discrete. The next one we're going to look at will be continuous. Hi guys, so I wanted to kind of demonstrate with a nice graphing utility what it looks like to graph a function and its inverse. I think it's really elegant if we can use technology that does things really a lot quicker for us. So I wanted to explore this really kind of simple equation, y equals x squared. It's just the parent function for a parabola. So we've already been kind of building this idea that okay, an inverse takes an output and matches it back to its input, so it kind of works backwards. And essentially, that's a matter of switching your x and y values. So on Desmos here, I'm just using desmos.com, their graphing tool. I'm going to just switch the x and y values in this equation, and I'm not even going to solve or simplify. Look at how sloppy I can be here. I'm going to say x equals y squared. Okay, so here's my graph. Looking like that. So notice how it kind of looks like I took my parabola and threw it on its side like that. Let's play with a couple of more functions and see what's going on here. Let's say y equals, I don't know, x cubed plus 5. So the green one is my x cubed plus 5. And now I'm going to do the same thing of switching the x and y values just to see what happens, just for fun. So I get x equals y cubed plus 5. And I'm going to take away the parabolas for a minute. Okay, so if you're, having fun with this idea, keep, trying out some more functions and just make them up, go crazy, have fun. Even if you don't know what it is you're entering, it can be really exciting to see what the graph looks like. But what I want to start noticing is how these graphs look kind of symmetric. Right, so if I turn my head sideways, it almost looks like a reflection, one of the other over these different spots. And let's notice a couple of cool things. This point right here is where the x and y values are equal to each other. So appreciate that for a moment. This x is equal to this y value, and it's shared on both of the equations. And just to, belabor the point, I suppose, let's come up here. This is 0 comma 5 on the y-axis. And down here, I have 5 comma 0 on the x-axis. So I know that I switch the x and y values. So if you're thinking in terms of switching x and y values, let's go back to that point where they cross. If I switch those x and y values, nothing would actually change here. Let's see if the same thing is true for the parabolas. So I'm going to bring the parabolas back for a moment and zoom in at these points where they cross. Well, they cross at 0, 0. So that's a point where x and y are equal to each other. And they also cross up here at 1, 1, where the x and y values are equal to each other. I wonder what it would look like if I graphed y equals x. Okay, So this black line here is where y is equal to x. And I want you to notice how every single point is actually reflected over that line. And it makes sense if you're thinking in terms of inverses, how you switch the x and y values. You switch the input and output values and then kind of graph them. So your result are two graphs, the original and its inverse, and they're symmetric over the line y equals x. I'm going to get rid of the parabolas for a moment and bring back the cubic functions and zoom out a little bit. And we can see again down here where these two lines or two functions intersect, the equation y equals x goes right through that point where they intersect. And it's really because if you think about the equation y equals x, it's all the points where those two values are equal to each other. So we found that, the point where the function and its inverse, where they intersect, of course, x and y are equal to each other. And so that third line, y equals x, also goes through that point. And then you can see and appreciate, from a bird's eye view back here, that wow, these functions really are symmetric over the line y equals x. And so, if you're trying to graph a function's inverse, start by graphing maybe, the function itself, and then graph the line y equals x and see if you can kind of butterfly wing, reflect it over that line and be able to draw your inverse function really quickly. So just a couple of cool things to appreciate as you're learning about inverse functions.